So I was really interested in the talks that preceded me recently this morning for a couple of reasons. What both of these guys have been getting at, in a sense, is the shift that's taking place in the world economy, moving companies, particularly from sort of their historical posture, to actually developing and embracing what I would call a quantitative culture. When I was at Amazon, principal engineers at Amazon have to give an annual lecture to the engineering organization. The last one I gave there, I called Superstitious Architectures, How to Avoid Them. Amazon may be, in fact, from my experience at least, one of the most competent technology organizations on the planet in terms of running, diagnosing, and understanding large-scale distributed systems. But large-scale distributed systems are hard to get visibility on and to really understand, and they exhibit unusual phenomenon from time to time. And human beings, being what they are, have a tendency to latch on to superstitious explanations for phenomenon, for visible phenomenon that they don't understand the underlying cause of. And as competent an organization as Amazon was at the time, is populated by human beings. And as such, there was always a tendency to embrace superstitious understandings about what was going on in these large complex systems. And what we worked hard at the time was increasingly moving Amazon to a quantitative culture in which data trumped intuition. There's a reason that the words superstition and intuition rhyme. And intuition can be a good thing, but having data is a great thing, and having knowledge that derives from that data is a greater thing still. In Dr. Hazra's presentation, he shared some thoughts on sort of the integration of ubiquitous public data with private data to produce insight and knowledge. And what I'm going to be talking to you about here today, just to give you a little peek behind the curtain, is the kind of stuff we're doing at AMD to influence our thinking. We're both students of and users of big data. And I wanted to ask, before I delve into this too much, how many of you are using big data in your organizations today, big data tools and technologies? How many of you are using Hadoop specifically? Okay. Any of you using any of the NoSQL databases like Cassandra, Dynamo, CouchDB, or anything like that? So just a few, handful. Okay, that's more for my information. As I kind of walk through this, I'll present. We study Hadoop and we use Hadoop to study Hadoop, and you'll see kind of why that works that way in our particular case. And maybe, there we go. So I'm going to talk to you a little bit about what we do in AMD research, and particularly to deal with the issue that system design and processor design don't occur in a vacuum, and they're influenced by certain inputs and perspectives about things. And one of those things is we design systems to meet the needs of emerging applications and workloads and infrastructure software that's coming out. And I want to talk a little bit about what we're doing in that space. I'll talk a little bit, there'll be kind of an obligatory commercial near the end about some of the products and things that are going on, and what AMD's overall strategy and the shift that we're undergoing is within the organization. So the real challenge when you're thinking about the software and the workload space is how do you identify and measure the applications that matter? And there's a number of real big problems with this. First of all, the application space is vast today, and application churn is fast. In the marketplace, significant percentages of the world's compute capacity are running entirely proprietary workloads, and the churn on those workloads is very rapid. Gone is the day in which you could think of server workloads in particular as this stable stasis sort of situation where you had known applications that were running for extended periods of time. Now we're in a world in which application churn is fast because the technology and the IP running on these infrastructures is very often proprietary. There's an inclination to optimize the software design and architecture for specific platforms. And so, and there's a pressure on a lot of these companies to rapidly provide new features. And so churn is very rapid. As I mentioned, entirely proprietary workloads and not just well-known sort of commercial legacy enterprise workloads are running on these infrastructures. And here's another big problem. These workloads are distributed and malleable. And by that I mean compute location is fungible. It can be decided at runtime. Gone is the notion, in particularly in distributed systems, where you know that certain code runs in one location and other code runs in another location. Particularly as data sizes grow, it's more economical and performant to move compute at runtime than it is to move data. And so the partitioning of application logic sort of blurs the distinction in some ways between clients and servers in terms of compute location and the workloads that occur in these contexts. The other problem with some of these workloads is that configuration spaces for scale-out applications are very often huge. Entire research papers are being written on tuning Hadoop, as an example. Anytime you have to write research papers and it's a subject of academic research, tuning systems like Hadoop, you get the sense that, that the problem of configuration space is large. As I mentioned earlier, the fundamental issues of getting visibility on distributed systems is also an interesting challenge. And here's the other thing, because scale-out architectures are the state of the art in terms of large-scale computing, varying network topologies can have a very interesting effect, decisive impact, frankly, on the performance of some of these workloads. I/O in many of these workloads dominates even compute as an aspect of overall performance of these applications. And the other problem in doing this, is in looking at these kinds of systems, is just analyst productivity. There's a core competency that needs to be developed in terms of deploying, managing, and running these kinds of applications at scale in order to gain insight. Running Hadoop on a single node does not provide the same insight that running Hadoop on 3,000 nodes provides in terms of system pressure points and architectural challenges. And so just analyst productivity is an interesting challenge. Now, blowing through the question about sort of how do we figure out what are the applications that matter? Well, some things are just obvious. Big data is obviously a big deal. This is a search on Google Insights to see what the search frequency is for the phrase big data analytics. And you can see that somewhere in late 2010, the phrase big data analytics went from being in the noise and the statistical noise to having a hockey stick-like search effect. Obviously, it's huge now. And so it's easy to say, well, big data matters because clearly it's become a mainstream area of interest. But there's other ways to think about sort of what matters in the marketplace. And one way is to look at sort of the axes of compute intensity versus I/O and memory intensity. And here's a bunch of different applications and categories that we've scattered around a quadrant diagram that says, you know, here's sort of how these different workloads and applications, these building blocks that are being used to build service-oriented architecture, scale-out infrastructures, here's how these kind of fit within the overall landscape of compute intensity and I/O and memory pressure on these systems. That's one way to think about it. But another way is to think about focusing on what we refer to as amplification points. Software amplification points they're strategic software workloads which have a disproportionate impact on the overall ecosystem. In particular, amplification points tend to be containers of software where if you optimize around the amplification point itself, there's a disproportionate impact on lots of other applications and your ability to impact in a positive way those other applications as well. Here's some examples of amplification points. The web browser is an example of an amplification point. It is the application container that occupies most end users on clients most of the time. We find that even on niche markets like gamers who are running, enthusiast-like systems, more than half the time, even gamers are spending actually in their browsers. And so if you can impact browsers in a positive way from a system and a processor performance standpoint, you can have a disproportionate impact overall on the end user experience. And so any of these amplification points represent interesting points of insight to be influenced by when you're designing systems and processors. We're focusing on a number of key amplification points across these categories: the data serving space, the data processing space. Some people, when they say, you know, big data is a compound term that really represents two very different categories of functionality. There's low latency response serving in the big data space, which is really a set of applications designed to provide really low latency responses. These are building blocks for storing and caching data for large data sets to provide low latency responses to lots of users. And then there's the processing infrastructures, it's kind of the scale out batch runtimes, if you will, for doing big data processing. And this is a very different sort of long latency, high I/O, throughput-oriented processing application. And these are things like Hadoop and things like GraphLab out of Carnegie Mellon. Cloud management and provisioning, we think, are important amplification points. Hypervisors, as I've already mentioned, web browsers. And there's a number of domain-specific libraries, particularly as it relates to machine learning and the processing of unstructured data, which is increasingly a factor not just for search engines, but across the legal, the national security space, the litigation support space. All of those spaces are increasingly, document management are doing interesting things in the area of unstructured data processing. Now, what are we doing at AMD to kind of help with sort of grappling with all this? One of the things we've built is something we call the Synthetic Workload Analysis Toolkit, or SWOT. And the goals of SWOT were to reduce friction for gaining visibility on distributed systems. We wanted to make it easier for analysts to get their work done. We also wanted the ability to generate and execute synthetic workloads that are verifiably consistent with the measured behavior of proprietary workloads. Many of our customers are running proprietary systems. They'd like to share their information with us, but they can't let their IP walk out of the house. And so what we have the ability to do with SWOT is actually to build a statistical model based on observations of their running systems and walk out the door with a statistical model that's verifiably consistent in terms of the pressure points it puts on both the system and the processor itself, so that we can gain design insight for these systems even in the absence of having the actual IP that generated the statistical model. We wanted people to be able to model and measure the effect of varying network topology. We want to run these workloads, but we want to be able to play with the network traffic itself. We want to inject artificial latency. We want to inject artificial error and packet fragmentation behavior, and we want to understand how that impacts things, and we want to automate and make this easier for an analyst to sort of explore across a range of network topologies. We want to be able to model different network topologies so that we can sort of group machines in large clusters into different network performance characteristics, so we can model different data center topologies all within single proximate system configurations. We want to be able to automate the exploration of large configuration spaces. We don't want people to have to sit down and become super sysadmins to figure out how to properly tune their Hadoop infrastructure. We want them to be able to sort of probe and explore in an automated way and find, if you will, the optimal configuration. And obviously all of this to improve analyst productivity. We want to automate the analysis of these scale-out workloads based on automating the provisioning and deployment. We do dynamic Linux kernel instrumentation, so we can actually instrument the kernel and understand sort of what the breakout is between idle time, I/O time, actual compute time within these architectures. And then we want to automate the aggregation of all this data and make it easy to do visualization on it on the part of end users. We like, the entire thing, the entire application of SWOT is driven through a web console, so any of our analysts can sit down and kind of point and click their way through the kind of data they want to gather, the kind of configuration range exploration they want to do, and they can actually deploy then these workloads, and we'll talk about which workloads specifically. They can deploy these workloads on both cloud computing infrastructures, public cloud computing infrastructures. They can deploy them on private cloud computing infrastructures, all running on top of hypervisors, or they can deploy on bare metal clusters and gather everything from system level data all the way down to microarchitectural data and get insight on what's happening down at the actual core level within these systems. We, for integration, in addition to Hadoop and things like Memcached, building blocks for service-oriented architecture and big data applications, we like the Cloud Suite set of benchmarks. I don't know if you're familiar with Cloud Suite, but we think it's a reasonable representation of what's happening in data centers and what's happening in terms of the building blocks that are being used. I'm going to kind of get a move on here. Hopefully some of these slides will be available to the conference attendees. But across the range of data analytics, data serving, media streaming, web serving, document search, and software testing, these are all a combination of building blocks and specific applications that are representative of the kind of things people are doing. Now, what kind of data can we get out of this? We can get things like histograms of network packet size and distribution over time. This is an example of network packet size and distribution over time in a particular Hadoop run. This is, I think, a Terasort run within Hadoop. And so for system designers who are trying to understand how to optimize network behavior within a system, or for people who are trying to understand how Hadoop is going to impact their network, you can generate these kinds of visualizations. If you want to inject 300 microseconds of network latency into your network and see how that impacts Hadoop at different map worker levels within your infrastructure, you can get a look at that kind of thing. If you want to see at node level metrics, what's the DRAM bandwidth being consumed at different levels of concurrent users. This is 700, 1,000, and 1,200 concurrent users for a PHP-based web application that's kind of a representative application for the kinds of interactive applications people are doing. It's a very Ajax-y kind of application. You can get this kind of visualization. If you just want to understand why your cores are stalling and what it's waiting on, you can see the distribution of reasons behind core stalling. And what's interesting to me about this one in particular, if you look at this bottom line of graphs here, you've got core 0, 1, 2, and 3 in a quad-core system. But if you look on the left, you can see that the graph looks very different on the left, and all the other cores look basically identical. Core 0 looks very different. And so you get a sense for, hey, maybe there's a case to be made for asymmetric cores in a multiprocessor part. Or maybe there's something else going on in the system that we need to dig into to try to understand why, when this particular node is running a single workload, we're having very differing behaviors on these cores. We can, generate graphs that show, kind of a thumbprint with a stall cycle breakdown showing why things have stalled and sort of how different kinds of applications look differently and where the resources are being consumed. In addition to sort of generating this kind of data, we're doing other things to kind of influence our thinking. We've done large-scale crawling of open source repositories, and we've processed many billions of lines of code across a bunch of different product categories. And we've done things like, where is the non-branchy code? Where does the non-branchy code exist in the wild? Because if you want to do compute on APUs or GPUs, branchiness is a bad thing in terms of maximizing performance. And so we went looking, where does non-branchy code actually exist in the wild, just to kind of inform our perspective. And you can see that in the sciences, obviously, traditional HPC spaces, there's a lot of non-branchy code. But interestingly enough, there's some mainstream spaces like speech processing and machine learning that have kind of a existence density, what we call an existence density, which is the lines of code versus the non-branchy loops that exist within the code. In the same sense, where's the arithmetically dense loops in this non-branchy code? And so you can see kind of where arithmetic density is. These are characteristics that have an affinity for GPU and data parallel style processing. And so we're actually, to the point was made earlier, we're amassing publicly available data as well as our internal experimentation to kind of influence our thinking about what matters. We're also in the midst of a very large-scale web analysis where we're doing dynamic analysis on the top 1 million websites in the world. We're going to actually render each of these websites, and we're going to gather a massive database that gives us insight into the implementation details on every one of these websites, as well as the performance characteristics across a variety of browsers particularly focusing initially on the open source browsers. We've done some preliminary work by doing some dynamic analysis of what's at the Wayback Machine, the Internet Archive, and you can see some interesting data here about computational overhead and web page implementation over the last several years, and what's happening in terms of more and more use of rich computational characteristics within web browsers in terms of the implementations people have actually done. So we're focusing on these amplification points. We're aggressively exploiting automation to amass large amounts of data to inform our thinking, and both internal data that we produce through our own experimentation as well as using publicly available information. As you guys may know, we recently acquired a company called SRII, and we're doing some interesting things in the area of server architecture, system-level architecture and servers. That was driven in part by the sort of large expected CapEx expenditures and scale-out data centers over the next several years. With a SRII solution, you can actually compress your entire infrastructure down to a 10U rack. We're participating in the DOE's Exascale project, and we're also moving to an SOC, a very much more agile SOC sort of design methodology, and we're delivering products into a variety of spaces. We're optimizing our designs based on amassing data and focusing on amplification points. We have an IP portfolio that ranges across a wide variety of spaces, including heterogeneous computing, and a bunch of work we're doing in APUs in that space. And we're actually in the process of transitioning to a much more agile, flexible SOC design methodology that's going to make us really much more adaptable in terms of our product design and our ability to get to market rapidly. So,
very good talk, Kate. Thank you.
Yep.